So now, today we are going to explain a topic, comparison of potential variations associated with quantum dynamics of electron. What it means that when we're treating electron as a quantum particle, what happens to its potential and the other parameters associated with the potential. So we judge the parameters by our formulation, we judge the potential variations, and then check that how much difference between the original potential and this potential has occurred. So actually, when the electron is treated as a quantum particle, its potential does not give the exact values by analytical formula. So that's why we need to correct that values for getting exact values. We can say that this is like a perturbation, but this perturbation is must, or we can say this perturbation is very much important when we are dealing with high density problems. When the electrons are so much electrons we are having, then what happens? These effects are dominant. The perturbations are dominant. These are not the small perturbations. So coming towards the group members, Mohammad Farooq, myself, Zainab Amjad, Awais Ahmed, Mubashir Israr, and we are working under the supervision of Dr. Omar Rahman and the co-supervision of Dr. Zizwan Akram. Now moving towards the outline. What's our outline? Introduction. First, we are going to introduce our topic. Then model which we have used. We will explain the model which we have used. And then work done by us, what work we have done, and what are the results, the fourth heading. And then we will conclude our discussion. And after that, we will show the references from where we have took the data and explained it, used it for our formulations. Introduction. Now, quantum hydrodynamics model or QHD model. It is a quantum mechanical model in plasma physics where we add quantum contributions of the quantum corrections to the classical Newton's second equation. Newton's second law is equal to ma. It's very simple. But when we are dealing with quantum hydrodynamics model, we can't use that simple classical Newton's second law. We add the quantum corrections in that, and then we get an other formula that is called quantum hydrodynamics formula. What is meant by hydrodynamics? Hydro means fluid, and dynamics mean motion. तो जब फ्लूइड की मोशन को स्टडी कर रहे हैं, यानी पानी है, पानी के मोशन को स्टडी कर रहे हैं, तो फिर हम हाइड्रोडायनेमिक्स का वर्ड यूज करते हैं. So many people don't understand what is meant by quantum hydrodynamics, so I am opening it that what does each word mean. So quantum hydrodynamics deal with the fluid of electrons or the Fermi particles like electrons, spin 1/2 particle. So quasi neutrality condition. Quasi neutrality condition actually hold on the plasma that what is this condition? We are having the positive ions and negative ions both in plasma. So under the quasi neutrality condition, it is must to have the equal number of negative charges and positive charges, that the net charge or net current should be zero in the plasma. That's why we will consider it plasma. So Fermi-Dirac statistics. Fermi-Dirac statistics. What are the Fermi-Dirac statistics? For Fermi-Dirac statistics, we add up the spin. For the Fermi-Dirac statistics, we add up the spin of electron or the Fermi particles, and we check the contribution of quantum current generated to the Fermi particles. So Fermi-Dirac statistics are simple. Local density approximation. When we are having a constant density in the plasma, that we are not having a space-varying density, then local density approximation is a method which is used to approximate the exchange and correlation energies that are affecting the original potential. So this method we have used in our presentation or our project for getting the exchange correlation potential analytical numerical formula. So our model consists of a heated conductor across which we have applied a potential difference of 10,000 volt. and we created a quantum plasma environment. Actually, the quantum plasma environment is created where the exchange and correlation potential effects are dominant. Ordinary plasma have not the dominancy of these effects, but when we are having the quantum dynamics or quantum plasma, like in the conduction band of a conductor, as we are studying here in the helium burning. So these are the models where we are studying this quantum plasma, and actually we are dealing with the non-relativistic quantum dynamics. We are ignoring the relativistic effects. If we add relativistic effects, the equation becomes more complex and the calculations are more complex. So that's why we didn't move there. So then our model have some specified values that chemical bonds are creating the potential 242.8 volt, and applied scalar potential is 10,000 volt. Initial number density of electrons is supposed to be 10 to the power 14, and temperature of plasma environment is supposed to be 5,000 Kelvin, and Fermi temperature is 10 raised to power 4 Kelvin. So work done by us, what we have done till now: general relation for number density. We have produced the plasma current relations. We have produced a general relation between density ratio and potential. We have studied the low density dynamics of plasma environment. We have studied the high density limit dynamics, spin unpolarized condition for the plasma, and also the spin polarized condition for the plasma. Now, how can we apply the quantum hydrodynamics model? Simply, we have the equation of motion F is equal to ma. So sum of force density is equal to sigma F is equal to me ne dv by dt. Ma, but here the force densities are considered, so ne is multiplied, any number of atoms or number of molecules, number of particles per unit volume. So we are having the three forces: electric force, Fermi pressure is the perturbation, and the exchange and correlation also perturbation. So we are adding up. So formula for the Fermi pressure is del P, and the exchange correlation formula Ne into del EXC LdA. And also we have the electric force, but here we have ENEE, because electric force we know that, but E is then put to be del phi here at down. Now what happens that we are having ME, mass of electron, but when we are dealing with the phase velocity of waves, then we know that the Fermi velocity of hot electrons is very high than the phase velocity of waves. But we are studying the waves. मैंने पहले कहा कि हम फ्लूइड को स्टडी कर रहे हैं, तो जब पूरे फ्लूइड की वेलोसिटी की बात करते हैं तो वो बहुत कम है एक सिंगल इलेक्ट्रॉन की वेलोसिटी से, क्योंकि वो जो इलेक्ट्रॉन्स वेव बना रहे हैं या जो उनका वेव फ्रंट है उसकी वेलोसिटी बहुत कम है बनिस्बत इलेक्ट्रॉन की वेलोसिटी की, क्योंकि हॉट इलेक्ट्रॉन्स हैं और जब टेम्परेचर हमने इतना ज्यादा 5000 केल्विन का अप्लाई किया तो इलेक्ट्रॉन्स बहुत तेजी से मूव करते हैं, ठीक है. So that's why due to their motion or their speedy motion, we can ignore the mass of electron here. So me approaches to zero. So this term here on the left side goes to zero. Now differential equation becomes ENE minus del P minus NE del EXCLDE is equal to zero. And we are putting electric field equal to del phi, or the gradient of scalar potential. So equation changes and we get NE del phi minus del P minus NE del EXCLDE. Now, if we take the momentum balance equation, actually, I told you that this equation, quantum hydrodynamics model ki jo equation hai, it is also called as the momentum balance equation. So we are dealing with the Z component only. We can take X, Y, another component, but we are dealing with the Z component. So we convert this equation for the Z component only. Now, we know that the differential partial of partial Z is same in the three terms. So we take it common. And when we take the integral of this, then the central thing, as we know that dx over dt is equal to 0. If dx over dt is equal to 0, तो फिर x क्या होगा, एक constant के equal होगा, x is equal to constant, because the derivative of the constant term is always equal to 0. So इसका derivative 0 है, so it is equal to a constant. if we put an initial condition that when phi is equal to 0, Fermi pressure is also equal to 0, and exchange correlation effects are equal to 0. That is when we are not applying the potential, to automatically we have the Fermi pressure and exchange correlation potential equal to 0. So that's why the constant is got 0. So we put this constant equal to 0. So we get E phi minus 1 over NEP minus EXCLDE. Now, this is the relation which will be used for plotting the graphs. So now, what about the current relations? क्योंकि हमने quasi neutrality condition define करनी है, IE is equal to II करना है, तो इसका मतलब है कि उसके लिए current relations चाहिए. So what about the production of current relations? We are producing the current relation. Current relations, as we are treating the ions as a Bose-Einstein statistics, bosonic particle, or we can say that these are not the quantum particles. So what happens that ionic densities will be explained by Maxwell-Boltzmann distribution function. Here we are not using Fermi-Dirac distribution function because we are not dealing with the spin effects of the nuclei or of the positive charges. So they have very less effect. That's why we're ignoring that perturbation. So so the Maxwell-Boltzmann distribution function is FIU is equal to A naught e power minus u over kBt. Now, we have the constant A naught equal to N naught into Mi into 2 over 2 pi kt. This is the simple mathematical relation which can be seen on the slides. So current relation for the ions are given simply by this. You can have a research paper, or we can check it in the reference we have put here from that reference article. So, but we are going to produce the current relation for electrons. We will solve the whole Fermi-Dirac statistics equation and solve the electronic current equation. Now, what happens when we are dealing with the condensed matter plasma physics or condensed matter physics? Electron quantum effect should use the Fermi-Dirac statistics. यानी आम करंट इलेक्ट्रॉन का जो है वो Fermi-Dirac statistics से नहीं आएगा, बोल्ट्जमैन से आएगा, लेकिन उसकी जो क्वांटम उसके अंदर जो क्वांटम फॉर्मुलेशन है या क्वांटम इफेक्ट्स जो ऐड हो रहे हैं, वो क्वांटम इफेक्ट्स हमारे पास Fermi-Dirac डिस्ट्रीब्यूशन फंक्शन से आएंगे. So Fe of u is equal to 1 over e power u minus mu over kBt plus 1. Now we know the simple formula that Hartree-Fock approximation current is equal to IE is equal to ENEVDA. Here the parameters are discussed that IE is the electron drift current caused by electric field, and VD is the drift velocity of electrons, N is the density of spin electron, and A is equal to area pi r square. So it gives the dimensions of the current ampere. So density of the spin electrons is given by N is equal to integral Fe of u dp over 2 pi h cut cube. Non-relativistic kinetic energy of electron is p square over 2m, simply p square over 2m, kinetic energy of electron from the Schrodinger equation, or simply we can say the momentum square over 2 into mass of electron. So here momentum can be got p is equal to 2mv u power 1 by 2, and we have seen that in the here n is equal to integral Fe of u. Fe of u is the electronic Fermi-Dirac distribution function, and dp is the momentum component. So here we got the momentum value p is equal to 2mv u into 1 by 2. So what we want to do, we want to convert this differential of momentum into differential of potential. So we take derivative on both sides. So now dp become equal to 2mv du over 2p. Now we put this value, we put the value of Fe of u here in this equation, and then value of dp. So we get this last equation, n is equal to integral 2mv du over 2 into 2mv u power 1 by 2 2 pi h cut whole cube e power u minus mu over kBt plus 1. Now we are only using the transformation between variables to solve the integral. notice that these variables x, dx, alpha, beta, these do not have any relation with physical interpretation. These are only to be let for solving the integral. Okay, so we are going to solve this integral, and we have interconverted the relations, the variables. So now here this second equation becomes that n is equal to 2me kb over 2 into 2 pi integral x power minus 1 by 2 e power x minus alpha plus 1 into dx. Now we know that kinetic energy is also 1 by 2 me vd square. Kinetic energy is p square over 2m, but it is also 1 by 2 me vd square. And momentum is 2 me u power 1 by 2. So what we need to do, we want to express Vd in terms of, we want to express it in terms of temperature. So now here, look that Vd is equal to P over Me, and now P is equal to 2 me u power 1 by 2. We put here and take square on both sides. We get this. P equals to this. Okay. So now we get xkbt. Okay. xkbt. So Vd become this one. So now current becomes equal to E into 2 me x power k x kbt power 1 by 2, this term, and integral have only this term in it. Okay, let us move forward. Current becomes this one after letting the variables and doing simple manipulations, and then we are going to take integral, and when we take integral we get this value. Number density of electron is Ne is equal to 2 into me kbt over 2 pi h cut square power 3 by 2. So current becomes, अब करंट हमारे पास ही आ जाएगा. So हमने करंट का रिलेशन डेवलप कर लिया. Now, applying cause neutrality condition, I've discussed before that what is cause neutrality condition. Cause neutrality condition is the equality of electronic current and the ionic current, or the equality of current due to positive charges and due to negative charges in a plasma environment. So we are equalizing the IE and II. So IE minus II is equal to 0. So we put both equations, current of II and current of current due to II. Here, divide by Ni, we get this relation. Then actually we are going to add the quantum effects. So this current is simple. This is these currents are not having the quantum effects in it, but due to quantum effects an additional current is produced. So we are going to add that initial additional current here, I quantum. So this is added here, and formula for I quantum is ENE, this one. Okay. So after doing a simple manipulation, we take under root mi over under root me common, and we get this thing. Let under root mi over me is equal to under root sigma. Mass ratio is represented by sigma, and Ne over Ni is represented by P parameter. That is the ratio of number density of electron to the number density of ions. It will represent that how much by increasing, it will represent the increase in the number density of electrons, because we are having the electron in the numerator. So we get this one, this equation, and after getting this equation, we rearrange and get the final relation, which is represented here. Now, after it, we are going to approximate the exchange correlation energy for low density dynamics. First of all, we are going to explain the low density dynamics. Actually, we have represented an article in our references that Perdue and Wang were the scientists who gave experimental curve relation, or we can say that gave a numerically analyzed solution for the exchange and correlation. This is the analytical solution. Exchange functional is the analytical solution, but this is the experimentally generated formula of the curve. Correlation potential or correlation functional is the experimentally generated, numerically analyzed curve formula from the curve, and where we know that n is equal to ENE. N represents the density, not number density. So charge into number density is equal to density. That simple relation. So sum of these two energies will become exchange and correlation energy for low density. These formulas are given for the low density. Okay. So EXC, low density LDA, is equal to EX plus EC. So now when we add this, we get this final relation. We have the parameter NE, number density. Actually, we have the parameters in this project, number density and potential. So all other parameters are depending upon this, but these are the constant. We'll let this constant equal to D. We'll let this constant equal to C. We'll let this constant equal to B. We'll let this constant equal to A. Only for the simplification, not any other reason. So now we get this final relation for the exchange and correlation density, exchange correlation potential for low density. So now using this exchange and correlation potential in the relation which we have developed before, here we have developed a relation here. We will use that exchange and correlation potential here. Here, what will happen? Now see. Now, when we put it here in this equation and we put the formula for Fermi pressure, what happens? We get this thing. Okay, and we know that MVFE square is equal to 2 kBT. Yani MVFE square over 2 is equal to half MVFE MEVFE square is equal to kBT, कि जो जनरेट हो रही है एनर्जी, थर्मल एनर्जी जो जनरेट हो रही है, थर्मल एनर्जी और काइनेटिक एनर्जी इलेक्ट्रॉन की इक्वल होगी, क्योंकि वो थर्मल एनर्जी काइनेटिक एनर्जी प्रोवाइड कर रही है इलेक्ट्रॉन को. ठीक है. So when we are applying the temperature, electrons are moving fast and fast. Because of that applied temperature, and the temperature is applied, it means that thermal energy is given, and when thermal energy is given, kinetic energy is increased, which means that thermal energy is providing the kinetic energy to the electrons. So that's why electron moving fast. So that's why we are using this relation, MEVFE square is equal to 2 kb TFE. So now when we use above relations in this equation, what happens? We get this equation here, and dividing by E, we simply divide by E. Now we came to know that these all are constants. These are constants and these are constants. So again, for simplifying, not for any other reason, for simplifying, we let C by E equal to D3, we let it equal to D2, we let this whole constant factor equal to D1, and the simplified form for the number density comes here. We solve this equation in Mathematica and get the number density equal to 7.6 to the power minus 90. Okay, by solving this equation. Now, what happened? Now we are going for the graphical explanation. As we know that we have formed here, adding electron current due to quantum effects, general relation between number, density ratio, and potential, we have formed a formula here between the P parameter, P is the parameter, Ni over Ni, and between U. Okay. We put number density, which we have got from there. We put number density here, and then we plot this whole equation. When we plot this whole equation, we get this second graph, this graph. What happens that when here you can see that low density limit have 2 into 10 to the power 23 number density, 4 into 10 to the power 23. This is the low density limit in plasma case. So मतलब ये 10 to the power 23, 10 to the power 30 इतने तक होगी, और जब 10 to the power 50 से above जाएगी तो वो उसको हाई डेंसिटी लिमिट हम कंसीडर करेंगे. ठीक है, अभी हम इसको लो डेंसिटी लिमिट कंसीडर कर रहे हैं. तो ये हमने इस इक्वेशन को जब प्लॉट किया, व्हेन वी हैव प्लॉटेड दिस इक्वेशन हियर with n is equal to this, which we got from the previous equation, what happened that we came to see that when we are increasing the number density of electrons, this is the number density of electron, और कह सकते हैं कि ये इलेक्ट्रॉन की नंबर डेंसिटी और आयंस की नंबर डेंसिटी में डिफरेंस है, n over n नहीं है. ठीक है, so when we are increasing the number density of electron, what happens that the potential goes on decreasing, or we can say increasing in negative quadrant or fourth quadrant. So this curve is like this, that it is decreasing because we are doing only one case. So this is decreasing curve. It means that when we increase the number density of electrons, the potential generated is decreased by this factor. That if we have number density 2 into 10 to the power 23, then approximately from here we have the decrease in potential 3.1 volt. Okay, because electron have negative energy solutions, so that's why this curve is flowing in negative quadrant. Okay, so going toward the first graph, it is the plot of exchange correlation energy with number density. Exchange correlation energy, we have developed this formula in previous slides, and now we are plotting this formula. What happens that when number density of electron is increased, exchange correlation potential increase in negative quadrant, or it goes on decreasing. Actually, it is not decreasing, it is decreasing the original potential. When we put into other formulation, it decreases the original potential. It is its values are negative, but it means that it is decreasing the original potential. So now approximation of exchange correlation energy for the high density limit dynamics spin unpolarized. So now again from the Perdue and Wang article, we have chosen these two, exchange functional and the correlation functional. Now what happened that here we got this different formula for the high density limit dynamics. That formula that is used for the low density limit dynamics is not useful here in the high density limit dynamics. Okay, so now what happened? So what happened that here we are using this logarithmic formula for the correlation function. You can check that here the exchange functional is only changed by a single parameter Wn. Other function is similar to that in the low density dynamics. Now what is this Wn? Actually, the concept behind it that when we are using the low density limit dynamics, we ignore the spin effects of electrons, because the electron spin effects are not contributing so much in the potential in the low density limit dynamics. But when we are dealing with the high density limit dynamics, the spin effects of electrons are so much contributable. They are contributing very much part of their energy in the original potential. So what happens that we are considering the spin here, but here the spin is 0. Why the spin is 0? Why we are using the spin unpolarized? Now think about it, that if the electrons, suppose we are having 20 electrons in a material and 10 electrons are having -1/2 spin and the other 10 are having +1/2 spin, what will happen? The net spin will be 0. So here in the spin unpolarized case, we are considering that spin is not polarized to -1/2 or +1/2. It have equal spins. We are having equal spins of electrons for +1/2 and -1/2. That some electrons have the +1/2 spin, and the same amount of electrons also have -1/2 spin. So now moving forward, when we put this WN formula also is from the Purdue and Wang article. When we put S is equal to 0, net spin is equal to 0 here, WN becomes 1. So what is S? NE up minus NE down over NE. Okay. So if NE up and NE down are equal, so S is equal to 0. That I have explained. So when we put S is equal to 0 here, WN is equal to 1. Okay. So now N is equal to ENE, similar to previous case, that this N is the density, charge density. Okay, charge density. And when we put N is equal to ENE, now this large NE is equal to number density. So exchange correlation, high density, local density approximation function will be EX plus EC. We simply add these two equations and we get this net result. Similarly, we use the log properties here. Simply ln of this is equal to 1/3 ln of this. Okay, simply. And now using the log properties here, we get this. Again, we are having this logarithm 3/4 pi e over ne. We use another log property, ln x over y is equal to ln x minus ln y, like this. And now exchange correlation functional or exchange correlation energy becomes this one after rearranging the terms. So now again, this is so large term. So what we have to do? Again, what I have discussed previously is shown here, that NE up minus NE down is equal to 0, because NE up is equal to NE down. up जो स्पिन इलेक्ट्रॉन और जो डाउन स्पिन इलेक्ट्रॉन है वो इक्वल है, ये जैसे यहाँ पे है. तो जब इसको इधर पुट किया तो S0 आया, S0 आया तो WN में पुट किया तो ये 1 आ गया WN. ठीक है. So simply which we have made relation here, ये यहाँ पे जो हमने relation बनाया है, now we are going to put values. Now we know that S is equal to 1, so S is equal to 0, so A of 0, B of 0, C of 0, and also we know that WN is equal to 1, so WN को यहाँ पे 1 put कर देंगे. So the final relation we are getting is this one. Okay, so now we are again going to simplify it. Simplify it that here we are having so much large constant. Can't we replace this constant with a simple constant for making it smaller equation? So that's why we are going to replace it. So when we replace this one with A, replace this one with B, this one with B whole, this one or H, here H, and G, I, and F, 5 constant. So the general relation of exchange correlation functional or exchange correlation energy we got is here. Now again, similar method which we have used in the low density limit dynamics will be used here. We will put the exchange correlation energy formula here in this equation. We will put the Fermi pressure formula here in this equation, and then also we will put another relation, MEVFE square is equal to 2kBT FE here in this formula, and we will get this relation. So now again, for making it simple, we replace A by E, we replace A by E by G2, we replace this term by G1, we replace this term with minus sign. Okay, this term with minus sign is replaced by G1. We replace phi, we don't replace phi, it's the potential, sorry. So we replace G over E, I over E with the new constants, and this equation is made. Now when we solve this equation for the potential shown in our model 10,000 volt, then we get number density is equal to 5.33 in 10 power 69. Now look at this one. Look at this one, that this is above 10 to the power 50. So that's why we are saying that this is high density limit, because बहुत ज़्यादा electron है. So again, we are going to put this number density equation, number density formula in this equation here, which we have produced already. Okay, now we will plot between potential and P parameter. What is P parameter? P parameter is Ne over Ni, number density ratio. So when Ne over Ni is increased, now you can say that curve is going more downward, and we can say that curve is expanded now. यानी जहां पर कर्व में उसकी वैल्यू मतलब एक्सपेंडेड इस तरह से है कि हाई डेंसिटी लिमिट डायनामिक्स है, बिकॉज हाई डेंसिटी वी आर हैविंग हाई डेंसिटी, सो द कर्व हैव द सिमिलर ट्रेंड। हालांकि देखा कि हमारे पास लॉगरिथमिक फार्मूला था, नंबर डेंसिटी में तब्दीलियां थी काफी, लेकिन फिर भी कर्व का बिहेवियर तकरीबन सेम आ रहा है। ठीक है, क्योंकि स्पिन अभी भी हमने जो है उसको इक्वल कंसीडर किया, इसलिए उनका नेट इफेक्ट अभी भी कोई खास मिल नहीं रहा। So we're not getting the effect of spin so conveniently, because we are considering that number of up spin and number of down spin are equal. Okay, so now plot of P. We have plotted this P here in this graph, that, and we can see that when we are increasing the number density ratio, what happens that the potential goes on decreasing, or we can say that the potential is increasing in negative quadrant, because electrons have negative energy solutions, they have already told. So that's why this curve is in negative quadrant. Does not mean that it is always decreasing. Okay, so coming toward the first graph, now here we can see the behavior is somewhat different. Okay, now we have a sudden decrease in the, or sudden increase in the negative quadrant in exchange correlation energy. Okay, because of the high density. So now moving forward, now here approximation of exchange correlation energy, ELDA XC. Similarly, for the spin polarized case, what is meant by spin polarized case? Spin polarized means that Ne up minus Ne down is equal to Ne. ठीक है, here the spin factor S is equal to 1 and Ne up is equal to Ne plus Ne down. Okay, so now what happens? Wn becomes 1.25992105 when we put 1 here. This term goes to 0, and here we get 2 power 4 by 3, and then divided by 2 we get 1.25, this thing. Now what happens that when we put this in the above formula, these values in this above formula, and also A of 1, B of 1, C of 1, these are from the article references given here, and same model is considered there. So now EXCLDFSP high density will become this thing. Okay, now EXCLDFSP is equal to ANE power 1 by 3 plus LNE power minus 1 by 3. Now we again we change this larger constants into the smaller constants. So we got the high density limit dynamics full spin polarized exchange correlation energy. Okay, now again we are using the similar method, is similar in the three cases: low density limit, high density limit spin polarized, high density limit dynamics full spin polarized. Only the parameters are varied. Method is same. So now for calculating number density, we put exchange correlation energy, Fermi pressure, and MV EV FC square is equal to 2 kBT Fe square in this above equation. So what happens that we get this equation. Again, we are going to simplify it. We will convert these values into the simple constants F1, F2, F3, F4. Okay, and then solving it in Mathematica, we get Ne is equal to 5.4127 to 10 to the power 64. Now check the difference. Here we had in the spin unpolarized case 5.33 10 to the power 69 number density, and now we are having 10 to the power 66 number density. So parameters are changed. That's why the value is changed. Now graphical representation, coming towards the second graph, when we plot P with U after putting this number density value, now what happens, that curve is shifted downward. यानी जहां पे 2 into 10⁻78 पे स्पिन अनपोलराइज्ड के केस में -8 पोटेंशियल आ रही थी, वेरिएशन की पोटेंशियल की वेरिएशन -8 आ रही थी, वो अब यहाँ पे तब्दील होके -10 पे चली गई है. So you're looking that spin effects are dominant at very high number density. So when we have used fully spin polarized case here, what happened, that spin effects are dominant and we are getting more potential variation here. The curve is shifted toward down. Okay, and also now here we can say that plot of EXCLD is given that this is the exchange correlation energy for the high density full spin polarized, and here we can see that more energy is released from the system. Okay, exchange correlation energy is released from the system, so it is curve is more. Here it's starting from -1000 values and there it was starting from 20, 30. Okay, so now moving towards the results. Results में तीन चीजें हैं. First one is comparison of the curves. Firstly, we have to compare the curves with each other. Okay. So electron fluid dynamics and variation of current. Then applications. So for comparing the curves, what we will do? We are seeing here that when we had this comparison is done between the full spin polarized case and the spin polarized case, not for the low density limit. Okay, we are comparing the curves between full spin polarized case and the spin unpolarized case. Now look at the upper curve. This upper curve represents the this upper curve represents the spin unpolarized case. Okay, it means that when the spin is not polarized to -1/2 or +1/2, what happens? The equal spin gives the net spin 0. So due to net spin 0, we do not get the spin effect dominant. And when the spin effects are not dominant, the upper curve have the less values than the lower curve. Because in the lower curve, we have also considered the spin effects, or we have considered the fully spin polarized case. That's why the values of the potential are increased in the negative quadrant, or we can say are decreased more from the system, or more energy is released from the system. Okay, क्योंकि स्पिन इफेक्ट की वजह से भी हीट एनर्जी की सूरत में, मुख्तलिफ एनर्जी की सूरत में एनर्जी रिलीज होती रहती. So what we have seen from this graph, or what we have seen from the whole system, that's non-linear dependence of exchange correlation energy. Here we can see that in this graph, we are not having a simple line graph like this or like this, or if we're making more simple, we're not having like straight line graph like this, like this, like this, like this. We are having a curve graph like this here as the curve is made. So curve means the non-linear dependence. Okay. So this is the non-linear dependence, increasing exponential dependence. This is the type of exponential dependence. Okay, so exponential dependence में values ज़्यादा increase कर जाती है. So straight line में values आहिस्ता आहिस्ता increase करती है. So due to exponential potential, the values are so much increased. Okay, now रूट्स ऑफ नंबर डेंसिटी. नाउ देखें यहाँ पर पीछे हमने बात की कि ये इस इक्वेशन को सॉल्व किया तो हमारे पास ये नंबर डेंसिटी आई. जरूरी नहीं है सिर्फ ये आए, इसकी बेबहा रूट्स आ सकती हैं. एज वी नो दैट n⁻⁻⁻⁻, n⁻⁻⁻3, n⁻⁻2/3. अगर क्वाड्रेटिक इक्वेशन हो तो उसकी भी 2 रूट्स होती हैं. यहाँ पर तो फिर हमारे पास ये 3 पावर्स आ रही हैं. सो वी कैन हैव सो मच रूट्स, but we have worked only for the one root, because plotting the graphs and solving the equations for so many roots is not so simple. Actually, our motive is to study the behavior, so that's why we are studying the behavior by using only one root. Okay, so now number density ratio and potential. व्हाट हैपेंड दैट नंबर डेंसिटी रेशियो यानी पी जो है और जो पोटेंशियल है, वी हैव ऑलरेडी सीन दैट दे हैव एक्सपोनेंशियल relation with each other, and that's why these are potential is increased when number density ratio is increased. Now larger quantum plasma environments. अब हमने कहा जी नंबर डेंसिटी बहुत ज्यादा होना और हाई डेंसिटी लिमिट या लो डेंसिटी लिमिट की दो बातें की। लो डेंसिटी लिमिट तो हम कह सकते हैं कि छोटा सा रॉड है, ये इतना सा एक हल्का सा रॉड है छोटा सा, उसमें जी चलो कोई 10⁻24 इलेक्ट्रॉन है, सपोज कर लो, कहानी है कौन सा सच है, उसमें कोई 10⁻24 इलेक्ट्रॉन है, तो उसमें से हम क्या कर रहे हैं, उसको टेम्परेचर अप्लाई कर रहे हैं जिस तरह हमने अपने कंडक्टर पे किया, उस पर टेम्परेचर अप्लाई कर रहे हैं, उसके ऊपर पोटेंशियल अप्लाई कर रहे हैं, तो क्या हो रहा है कि इलेक्ट्रॉन मूव कर रहे हैं, ठीक है। लेकिन डेंसिटी 10⁻24 तक ही है, 10⁻24 तक तो स्पिन इफेक्ट्स का नामो निशान ही नहीं पैदा होता, उसका इतना जिक्र ही नहीं होता, ठीक है, वो तो भूल जाओ। अब दूसरी बात करते हैं, स्पिन इफेक्ट का कोई तस्करा नहीं होता। दूसरा, लो डेंसिटी लिमिट के लिए जो फार्मूलिज्म हमने लगा के ग्राफ प्लॉट किया, तो अगर हमने स्मॉल कंडक्टर की पोटेंशियल वेरिएशन देखनी है जिसमें नंबर डेंसिटी कम है, so what we will do, we will use the first formulation for low density limit, and when we are वर्किंग फॉर द लार्जर प्लाज्मा एनवायरनमेंट, सैटर्न की रिंग्स देख लें, जुपिटर के ऊपर जो प्लाज्मा एनवायरनमेंट है वो देख लें, ठीक है, उसके बाद न्यूट्रॉन स्टार्स को देख लें, जितने भी सितारे जो मरते हैं, जितनी भी उनकी वो फॉर्म्स होती हैं, उन सारों को देख लें, वहां पर जितनी प्लाज्मा एनवायरनमेंट्स हैं, many of them are the quantum plasma environments, and there is very high number density there, and when we are studying that plasma environment with very high number densities, then we will use the full spin polarized case for our high density limit, because it will give us the approximate results for that. So इसका बहुत बड़ा यूज है एस्ट्रोनॉमिकल फिजिक्स में, या कह सकते हैं कि एस्ट्रोफिजिक्स में, और उसके बाद प्लाज्मा फिजिक्स में। सो इट इज नॉट अ सिंपल टॉपिक, एक्चुअली ये तो हमारी एक जर्रा सी कोशिश है, इट इज अ वेरी स्मॉल, वेरी वेरी स्मॉल effort for approximating the potential variations of the potentials in high plasma environment or here on the in the conduction band or any other quantum plasma environment. Bahral, now non-dusty plasma and dusty plasma, actually we consider the non-dusty plasma, हमने कहीं पे डस्ट का जिक्र नहीं किया, डस्ट का जिक्र होगा तो quasi neutrality condition में डस्ट के लिए अलग से चार्ज into n पुट करेंगे, so we're not here confirming any the non-dusty plasma environment, dusty plasma environment. This is the non-dusty plasma environment we are having here, non-dusty plasma environment. But अब सवाल पैदा होता है कि अगर नॉन डस्टी प्लाज्मा एनवायरनमेंट के लिए मॉडल तो कर रहा है, लेकिन नॉन डस्टी प्लाज्मा भी एग्जिस्ट तो करता है, जरूर नहीं हर जगह डस्टी प्लाज्मा हो, कंडक्शन बैंड में कौन सी डस्ट होती है, नॉन डस्टी प्लाज्मा होता है। लेकिन अगर हम डस्टी प्लाज्मा को स्टडी करना चाहें तो फिर सवाल पैदा होता है, सो व्हाट वी विल डू, सो इट इज नॉट सो डिफिकल्ट, सिंपली जो हमने कॉजी न्यूट्रलिटी कंडीशन लगाई है उसके अंदर करंट आ जाएगा, जो करंट वो डस्ट पार्टिकल्स कैरी करेंगे उनकी एक टर्म ऐड होगी, उसके बाद इन करंट रिलेशंस को हम कंपेयर करेंगे, तो फिर वो डस्टी प्लाज्मा के लिए हमारे पास एक रिलेशन बन जाएगा। So these formulations can be used for the dusty plasma after simple manipulations. Okay, so ये भी इसका यूज है। एप्लीकेशन चूंकि मैं पीछे भी एक्सप्लेन कर चुका हूँ ये इलेक्ट्रॉन फ्लूइड डायनामिक्स में, लेकिन फिर दोबारा मैं बता देता हूँ कि कंडक्शन इलेक्ट्रॉन को हम स्टडी कर सकते हैं, वी कैन स्टडी इलेक्ट्रॉन्स एंड होल्स इन सेमीकंडक्टर्स, वी कैन स्टडी द सन, सन नहीं कि ये सूरज को हम स्टडी कर लें, सूरज किस चीज से क्या चीज है ये वो, लेकिन क्योंकि वहां पे भी टेम्परेचर बहुत हाई होता है, प्लाज्मा एनवायरनमेंट होती है, हम इस फॉर्मुलेशन को वहां पे लगा सकते हैं। सो ब्राउन ड्वार्फ्स, जायंट प्लैनेट्स, व्हाइट ड्वार्फ्स, सुपरनोवा एक्सप्लोजन, न्यूट्रॉन स्टार्स, ये जो मैक्सिमम है इसके अंदर, ये जो है हमारे पास ये इसी चीज से रिलेटेड है कि जो सितारे मरते हैं तो उनकी जो बात प्लाज्मा एनवायरनमेंट होती है उसकी बात कर रहे हैं, क्योंकि हीलियम अपनी सारी बर्न कर चुके होते हैं, तो हाई टेम्परेचर पे जब उनका कंडेंस्ड प्लाज्मा बनता है तो फिर हम ये फॉर्मुलेशन लगा सकते हैं। लेकिन एक और बात बता दूं कि हमारा जो मॉडल है, मैं दिखा देता हूं, ये जो हमारा मॉडल है इसमें हमने ये लिए हैं वैल्यूज, इसका ये मतलब नहीं है कि ये फिक्स है, ठीक है। अगर आप किसी और प्लाज्मा स्टडी करना चाहते हैं, यू वांट टू स्टडी एनी अदर प्लाज्मा एनवायरनमेंट, कोई भी और प्लाज्मा एनवायरनमेंट को आप देखना चाहते हैं, तो आप उस प्लाज्मा एनवायरनमेंट के हिसाब से ये पैरामीटर ले लेंगे। सपोज करें कि सन का टेम्परेचर आपने किसी जरिए से मेजर कर लिया, आपने कहा जी ये तो 25,000 वोल्ट है, तो इस फॉर्मुलेशन में आप इसको 25,000 वोल्ट से रिप्लेस कर देंगे। ठीक है, तो मैं वही बात जब आखिर में इधर कर रहा हूँ कि न्यूट्रॉन, स्टार, सुपरनोवा, एक्सप्लेन, इनके मुताबिक कंडीशंस लगेंगी, इनके मुताबिक मॉडल किया जाएगा और फिर ये फॉर्मुलेशन यूज कर सकते हैं उसकी पोटेंशियल वेरिएशंस देखने के लिए। नाउ कंक्लूडिंग अवर टॉक, वी कैन से दैट हियर the potential variations for the spin polarized cases and spin unpolarized cases for the high density limit are different, because when we are having so much high number density, spin effects can't be ignored, spin of electron, and for the low density limit spin का तो कोई तज़किरा ही नहीं है, क्योंकि वहां पर स्पिन की बहुत स्मॉल कंट्रीब्यूशन होती है, बहुत स्मॉल परटर्बेशन होती है, उसको हम नहीं करना चाहते बीच में शामिल। सो now the comparison of curves also told that there is a difference between the spin polarized potential variation and spin unpolarized potential variation. So this model can be used for studying the plasma, non-dusty plasma and dusty plasma environments having high number densities and low number densities. That's why we are formulating the two theories, one having small number densities and one having the large number densities. And in large number densities we have also formulated two theories, one for the spin polarized cases and one for the spin unpolarized cases. So these are the references. Here we can see that first of all we used the quantum hydrodynamics for plasmas, Thomas Fermi जो मैं जिसको मैंने पहले जिक्र किया, and then the JP Purdue and Wang research article जिसमें से हमने exchange correlation potential की values वो रिलेशंस उठाए। उसके बाद देन रिव्यू ऑफ अप्रोक्सीमेशंस फॉर द एक्सचेंज कोरिलेशन डेंसिटी फंक्शनल थ्योरी, इसमें से हमने अप्रोक्सीमेशन एक उठाई, वो वाली जो फुल स्पिन पोलराइज्ड के लिए थी। नाउ डी.ए. मेंडलिस एंड एम रोजनबर्ग, डिपार्टमेंट ऑफ इलेक्ट्रिकल कंप्यूटर इंजीनियरिंग, ये जो कॉस्मिक डस्टी प्लाज्मा है, दिस इज अ बुक एंड वी हैव स्टडीड इट for the applications के इस प्लाज्मा की applications क्या हो सकती हैं, and then influence of quantum effects associated with electron potential variation of charge dust। अब ये डस्टी प्लाज्मा की भी हमने पढ़ी है, लेकिन हमने डस्टी को डील नहीं किया, इसलिए हमने उसमें से डस्ट चीजों के डस्ट की जो फॉर्मुलेशन है, तो जो हमने क्वांटम हाइड्रोडायनामिक्स की इक्वेशन उठाई वो यहाँ से उठाई, लेकिन फर्मी प्रेशर के फार्मूलाज हो गए और उसके बाद फर्मी प्रेशर का फार्मूला हो गया, आयोनिक करंट का फार्मूला हो गया, और बहुत सी बेशतर चीजें हमने इस रिसर्च आर्टिकल में से उठाई। एंड देन now we used a modified local density approximation। तो local density approximation का जो फार्मूला है कि local density approximation की डिटेल जो है कि ये क्या होती है, वो हमने इस रिसर्च आर्टिकल से स्टडी की। एंड स्टैटिस्टिकल प्लाज्मा फिजिक्स, जो करंट रिलेशन हमने इलेक्ट्रॉन का डेवलप किया, तो वो कैसे डेवलप होता है, उसके लिए क्या कंडीशन है, वो सब हमने इस रिसर्च आर्टिकल में से किया। सो दिस ऑल वाज फ्रॉम आवर साइड एंड नाउ योर क्वेश्चंस आर वेलकम्ड। थैंक्स।